All right, hello. So I'm going to talk a bit today about reinforcement learning. And I should mention that I was formerly a graduate student at LIDS just a few years ago, it seems. And the topic I'm going to talk about today actually relates to work I did here as a doctoral student. When I was advised by our host, John Sisiklis here. At the time, Dimitri Bertsikis was also quite engaged in this area, and I interacted a lot with him. And so, it's a great opportunity to be here today and sort of talk about recent progress in the stuff that we were involved with so many years ago, and to honor Dimitri and the other LIDS faculty that we're here to honor over these 2 days. I should also acknowledge I interacted a lot over the course of my time here with Sanjay Mitter. In fact, when I first started as a PhD student here at the beginning of my first academic year, I wrote Sanjay saying, can we meet? I'm interested in the kind of work you do, and it'd be interesting to talk to you about research opportunities. And a few months later, on the evening of December 24th, he replied to me saying, I'm available tomorrow if you'd like to meet to talk about research. So we should, recognize that we have some visionaries in our that our LIDS faculty are visionaries, and in the case of these two fellows that worked on the topic I'm going to talk about today, one area that they've worked on in the past is this parallel and distributed computation. They wrote this incredible and comprehensive book on the topic in 1989. It went out of print in 1996, right? And then it became an interesting and important topic in 2006 with the advent of cloud computing. So these fellows are so far ahead of their time that they're forgotten by the time the topic becomes eminent. Similarly with the topic of reinforcement learning, these guys got into this in the mid-90s. Their work on this, or the book they wrote on this to try to encapsulate this area, was probably forgotten by the mid-2000s. And then the topic of reinforcement learning emerged and captured the imagination of the public just a few years ago. Okay, so it's sort of an interesting trajectory in both cases. So what I want to talk about today is what is reinforcement learning, and I'll start by discussing what reinforcement learning is, right? Because there's a lot of confusion I find with different people thinking of reinforcement learning as being different things. And that's all okay, but let's talk about what we're going to talk about. So one thing is reinforcement learning is a problem. And there's a reinforcement learning problem that you can think about and work on. Reinforcement learning is also used to refer to a community of researchers who work on this problem. And finally, reinforcement learning is used to refer to methods developed by this community of researchers. To add confusion to the picture here, some of these methods are used for other problems that are not reinforcement learning problems, right? And so when you include that all under the umbrella of reinforcement learning, it casts a really broad net, and it can be confusing, what reinforcement learning is about. And I think it's okay. Right? It's okay to use the name in this broad sense, but it's important to distinguish these different uses of the name. And in particular, what I'm going to talk about today revolves around the reinforcement learning problem. Okay, so what is a reinforcement learning problem? The reinforcement learning problem is a problem faced by an agent interacting with an unknown environment. Okay, the agent takes an action and observes feedback from the environment, and does this sequentially over time, and at each time also realizes a reward, right? The reward is a signal internal to the agent that tells the agent, that represents how much the agent likes or dislikes what it sees in its observation, right? So this is a reinforcement learning problem, the problem of an agent taking a sequence of action, learning about the environment, and trying to improve over time the way it behaves in order to improve its rewards. All right, there's many examples one can provide for reinforcement learning. One arises in robotics. And so you could imagine a robot trying to learn how to perform a particular task, right? You reward the robot with completion of the task. And over many, many tries of completing the same task over and over, the robot might learn how to do it successfully. In web-based services, many of the problems we face in web-based services can be cast as reinforcement learning problems, because in a web-based service, you interact with users and you try over time to improve the nature of the interaction and improve how well they are served. And an example of this could be online education, right, where a reinforcement learning agent could learn over time how to design a curriculum to improve test scores of students that it interacts with. All right, so I should mention that reinforcement learning is somewhat distinct from other areas of machine learning, and part of the distinction is the technical problem formulation, but there's also a philosophical distinction that I think plays an important role and distinguishes the culture of this field. And this difference is captured by this statement, which is similar to statements that Harry Clough used to make. Harry Clough was an early reinforcement learning researcher in the 1960s and 70s. And he used to say that reinforcement learning is different because other learning paradigms are about minimization, whereas reinforcement learning is about maximization. Okay? And so what does he mean by that? Well, as anybody at LIDS would know, you can change a maximization problem or minimization problem into a maximization problem by changing the sign of the objective function. But what he meant actually was quite important, I think. And that is that the mindset people had around machine learning and adaptive control and other areas that sort of involved learning at the time involved getting a machine to do what you want it to do, okay? So you have a data set, you want the machine to develop a model that matches the data, right? Get the training error down to 0, right? You're telling the machine to minimize error, get it to match the data, right? Get your model to match the data. In something like adaptive control, the typical framing of the problem is where you have a trajectory you want an object to follow, and you have the object you have the object progress over a trajectory and try to learn over time how to get closer and closer to following that prescribed trajectory. All right, so reinforcement learning came along and took a more blue sky view of the learning problem, where the designer may not have any idea in advance what it wants the agent to do. Right? I don't know what I want the agent to do. I want the agent to get good rewards, but I have no idea how good the rewards can get. All right, so with that view, although it permeates a philosophy and really drives a different mentality toward research in reinforcement learning, which I think is important. And you see facets of that today with all the impressive work done in reinforcement learning. For example, there are systems based on reinforcement learning algorithms that play chess better than grandmasters. And we have grandmasters analyzing the moves made by these systems and writing books interpreting why they make these moves and why humans didn't think of doing this before, right? So this blue sky view of research leads to stuff like this that is sort of somewhat more out-of-the-box thinking. All right. A lot of the excitement about reinforcement learning over the past few years has been driven by interest in creating artificial general intelligence. So what is artificial general intelligence? The idea is to develop a system that can achieve human-level competence across all intellectual tasks. Okay? All intellectual tasks. So one piece of software can do anything as well as a human. And the interest in RL is driven by a belief that RL is a promising approach to generating artificial general intelligence. Okay, so one obstacle here, and this is what I'm going to touch on today, is that although reinforcement learning algorithms have produced quite impressive results, they have tended to be quite data inefficient. Okay, and what I mean by that, well, it's for this reason that reinforcement learning algorithms that have delivered impressive results have typically been applied to simulated systems, but not real systems. Because with simulated systems, you can generate as much data as you like. Okay? And if you look at these systems that work with simulated data and think about how much time an agent would take to learn something similar interacting with a real system, a physical system, you typically find that in real time, agents are taking thousands to millions of years to produce the kinds of results you're seeing. Okay? So an important obstacle in reinforcement learning is this data inefficiency. And a lot of activity in the field today revolves around getting these numbers down into days and weeks rather than thousands or millions of years. All right. I should mention one interesting aspect of the reinforcement learning community is that it's traditionally been somewhat divided into two cultures. All right? There are the hackers that tinker with computers and produce impressive simulations and demonstrations. And then there are the LIDS types who abstract and study algorithms and produce insightful results. Until recently, there hasn't been as much of a connection between these two areas as there probably should be. But this agenda for data efficiency, the need for data efficiency really calls for developing a deeper understanding of reinforcement learning and leveraging that to guide the design of reinforcement learning agents that are more data efficient. Okay. So this is a really important area pushing forward. Okay, now there are a number of areas of study in reinforcement learning that can be real game changers in terms of data efficiency. And there's exploration, the use of hierarchical representations, the use of richer feedback. Traditionally reinforcement learning systems had a focus on learning from observed rewards, but you can actually learn much faster by using richer information from observations. But there's a lot one could potentially talk about here, and I'm interested in all these topics. But over the past decade, I've done a lot of work in exploration, and I'm going to talk about some of that today. Yeah. All right. Now, exploration can be a huge game changer in the efficiency of reinforcement learning, because if you do poor exploration, it can take you essentially forever to find a good strategy in a reinforcement learning problem. And even a simple example can illustrate the issue there. So this is a famous reinforcement learning problem. It's the cart-pole problem. And if you go online, you can download Python code for the cart-pole problem from many different sites. And it's typically the first control problem one considers in a reinforcement learning course. Now, we'll consider a formulation of this problem here where a robot is tapping a cart left and right and gets 20 seconds to try to balance the pole, right? And whether it succeeds or fails, the episode ends, and then you move on to the next episode, and the agent can get to try again, right? And over these repeated episodes of interaction, the agent tries to learn to balance the pole. It gets 20 seconds to balance. Now, the cart-pole problem in reinforcement learning is typically considered a really easy problem. So, you can download the cart-pole software, you can download just about any reinforcement learning algorithm and apply it to the cart-pole problem, and it'll solve this problem to our satisfaction, okay? But actually, there's an easy case of the cart-pole problem, which is the one you download, and there's a much harder case, which I'll talk about now. All right, so in the easy case, the agent gets continual feedback from what it's doing. So in particular, as the agent is getting the pole higher and higher, you tell the agent, warmer, warmer, you're doing better, et cetera. And eventually it learns to balance the pole, right? The feedback could be at each time something like the distance from the goal state. Okay. Now, there's also a hard problem and a hard version of this, and you can turn this problem into a very difficult problem by changing the feedback structure to one that's particularly sparse. In particular, suppose you only say good robot when the robot has the pole perfectly balanced, but don't give any feedback otherwise, right? So then, how does the robot learn? Well, it's sort of scrambling in the dark, trying to balance a pole, not even knowing what you want it to do, and hopefully eventually it'll figure out what you want it to do. Okay. All right, so when you take a problem like this and show it to reinforcement learning researchers, it's interesting to me that the community bifurcates. There are people that say the cart pole is trivial, this is going to be an easy problem that can be solved by any algorithm, right? And then there are people who say this problem is not possible, no algorithm can solve it, because you're essentially saying I have to guess the right binary sequence of left and right taps that will balance the pole. And how can you guess the right binary sequence? It's like finding a needle in a haystack. Okay, so it turns out that the right answer is sort of neither of those extremes. None of the typical reinforcement learning algorithms you'll download from the web will solve this problem in reasonable time, right? But the problem isn't impossible either. If you make the right tweak, which I'll talk about, you can solve this problem efficiently. All right, so, and the tweak involves better exploration. So most of the common reinforcement learning algorithms, the ones you would download from the web, use a form of exploration called dithering, where essentially the agent's trying to learn. At each time, the agent is taking actions it thinks should be good based on what it's learned so far, but it adds noise to them, right, in order to induce some exploration and try new things that it hasn't tried before. But even after 1,000 trials of this cart-pole system, such an algorithm that does dithering exploration won't learn anything useful. Okay, so what I'm going to talk about is another form of exploration I call deep exploration, where the agent seems to be learning something over episodes of interaction. There's 500 episodes. And after 1,000 episodes, the agent will have learned to solve the task essentially perfectly. Right? So I'll talk a little bit about deep exploration, which is a broad concept that classifies exploration algorithms and reinforcement learning, and what makes a algorithm do deep exploration and why that can lead you to solve a problem like this. Okay. Okay, so what is deep exploration? And why is it different from dithering? So this cartoon is meant to illustrate the concept in a simple way. Suppose you consider a reinforcement learning problem faced by a mouse, right, that day after day, each day arrives at a maze, gets to navigate in the maze to try to find rewarding feedback, and then, at the end of the day, goes to bed, wakes up the next day, and goes back to the same maze. Right? Every day is an identical maze. Well, over its interactions, the rat can learn more and more about the maze and what in the maze might offer it reward. So suppose after some days, the rat has learned about everything in this white part of the maze, but has not learned about anything in this grayed out part of the maze. Okay? So this is what the mouse knows on day n. Given its knowledge, what should the mouse do? Well, the mouse doesn't know what's in the gray area, so it could make conjectures. One is that, hey, there might be something very attractive in the gray area. Maybe I should check it out. Or it might be pessimistic and say, hey, that's not a good idea. There might be something really bad there. Let's avoid that. Okay, so what should the mouse do in this situation? Well, there's really two things that the mouse should consider, right? Two alternatives. One is to make a beeline for the cheese because it'll get some reward, right? It knows it can get to the cheese. It knows it can get some reward. And the other is to make a beeline for the gray area because at least it'll learn something new, good or bad. Okay? Now, deep exploration is exploration that only allows for these two possibilities. What's the problem with dithering? Well, dithering is about adding noise. So if a mouse is in this maze and dithering, it's sort of moving around like a random walk, hoping it'll learn something new. And what happens when you're dithering is you're walking around this part of the maze you already know about, gathering data that simply reinforces what you already know. Right? What you want to do is avoid dithering, right? Because that's gathering useless data. You either want to do something that's rewarding, or you want to gather data that's informative. Okay, so that's the key to deep exploration. All right, so another way to think about this is the mouse can be motivated by reward or an opportunity to learn. And the mouse in one day takes many steps through the maze. It could consider what it can learn from its immediate step within the maze. And if it's trying to optimize reward over an immediate step, you can think of that as a myopic optimization problem. If you're trying to learn something over the next step, you can think of that as a myopic exploration problem. Now, what's important is that the mouse sort of plans ahead because it has some information about the maze, so to somehow look ahead multiple steps if possible. And if it's trying to get reward, what it should really be doing is solving a multi-period optimization problem, right? Like what steps do I take to get the cheese? And if it wants to learn something, well, this is what I call deep exploration. It should be planning multiple steps ahead so that it can make a beeline toward gathering useful information. Okay, so clearly, if you want to produce artificial general intelligence, you need to be doing deep exploration because it's hard to claim artificial general intelligence if you can't balance a pole. Okay. How to do this in a systematic and scalable way is an important topic in this area. Okay, and I'll talk more about that. All right, so here's an outline. So I'm going to talk a bit about the general exploration problem, not focused on reinforcement learning, but just the broad notion of exploration here. And then I'll talk about Thompson sampling as a heuristic for the general exploration problem, and randomized value functions as an approximation to that for the purpose of reinforcement learning. If I have time, I'll talk a little bit about going beyond Thompson sampling, because Thompson sampling is sort of a arbitrary heuristic that accomplishes deep exploration, but where you might be able to do much better, actually. All right, so here's how I think about a general exploration problem. You could think of it as a Bandit problem, if you like. But you have a channel, and you can think of theta as what is unknown about the channel, the parameters of the channel, right? You can apply an action, and it goes through the channel, and you see a response, right? And you do this over and over again, right? And through these multiple interactions, you learn more about theta, all right? And let's say we're trying to elicit a particular response from the channel, and we have a reward which is a function of the response, and we want to get large rewards, right? That's how we quantify our objective. All right, let's say we have a prior over the channel parameters theta. What's a learning algorithm? A learning algorithm is an algorithm that takes all the data we saw over the first L interactions and maps that to the action we'll take next. Right. You can define an optimal reward, R star, as the expected reward you'd realize if you knew what the channel parameters were and you chose the action that optimized for that channel. And we can frame the problem of exploration here in terms of minimizing regret for over a large number of time periods, where regret is defined as the sum of these differences between the optimal reward and the realized reward. And you take the expectation and sum over capital L time periods. Okay? Okay, so that is one framing of the general exploration problem. All right, so okay. So how do we design and analyze algorithms for that problem? Remember, an algorithm, a learning algorithm, there is one that takes our past data and generates the next action. Well, one thing we've been working on, which I think really builds on the kinds of things I learned from LIDS, but the kinds of things we work on as a community, is studying this through the lens of information theory, right? And in particular, it turns out that for any prior over channels and any learning algorithm, you can write down a bound on regret of this form here. Okay, for all priors and learning algorithms. And one of the powerful things about information theory is its generality, and so you can get results that sort of apply to everything. Right? But there are a couple statistics here that you have to quantify in order for this to be a meaningful result. So this last term here, I'm going to sort of ignore because it's sort of it's a tolerance term, and you can think of epsilon as being something very small. This rho of epsilon is a function of epsilon, and you can think of that as a notion of rate distortion, which depends on your prior and indicates the number of bits of information you need about the channel in order to make epsilon optimal decisions. And then this term here is an interesting term, this gamma term. I call it the information ratio, right? And that actually depends, it's a statistic that depends on both the algorithm and the prior, and it's meant to quantify the cost required per bit of information acquired about the channel. All right? Okay, so anyways, it's a very general result. And I should mention that this is sort of fun to work with because you got to think about all these different statistics, but this flavor of analysis is still in its infancy, but I find it very interesting. And one way in which, one thing that indicates how this is still in its infancy is I sort of vaguely define the information ratio here, but I actually have multiple possible technical definitions of information ratio, and I'm not sure which one is the best one to use. Okay. And there are a few cases where information ratio has been studied, and all this stuff has been sorted out. But I think there's a lot more of this for us to do. And but the cases that have been sorted out are sort of interesting. And one case is for the Thompson sampling algorithm, which is one algorithm for doing exploration. So let me explain Thompson sampling and then this relation to this information-theoretic view. All right, so what's Thompson sampling? Thompson sampling is one instance of a learning algorithm here. And the way Thompson sampling selects the next action based on the data you've observed so far is it computes a channel parameter, theta tilde, from the posterior distribution of the channel conditioned on the data you've seen so far. And then it applies the action that would work best for that sample. All right, so that's Thompson sampling, which is one learning algorithm. All right, and so just to offer an example of how Thompson sampling works, let me talk about Thompson sampling as applied to the linear bandit problem. And what's a linear bandit problem? The linear bandit problem is one in which the set of possible actions is a polytope, and the objective is linear in the action. Okay, so your unknown channel parameters here are these linear coefficients making up this vector theta, right? And the reward is your observation, and that's a noise-corrupted version of this linear function theta transpose x. Yeah. Well, in this case, you can show that Thompson sampling has an information ratio that's bounded by half the linear dimension. That's kind of nice. Right? That's an information ratio gamma. And when you plug this into the general information-theoretic bound I discussed, right, and sort out the rate distortion, you get a bound like this, where regret is bounded by the linear dimension, essentially times the square root of t. Okay. Interesting things about bounds like this is it doesn't depend at all on the number of actions, which is infinite here. It's the entire polytope. And I should mention that this is probably essentially optimal in its dependence on the dimension of the space and the number of time. Oh, t should be L here. Sorry, the number of time periods L. Okay. Actually, one open area here is to establish lower bounds. I'm pretty sure there should be a matching lower bound for this, but I haven't been able to show that yet. And so I'm waiting for some LIDS students to help show me how to do this. All right. Okay, so what have I talked about? So I talked about what I thought sort of an interesting way of viewing the general exploration problem, and how it can be analyzed through the lens of information theory, and how that can lead to very concrete results that are probably the best you can do in terms of quantifying how well exploration can work. Let's go back to the reinforcement learning problem. So in the reinforcement learning problem, an agent interacts with the environment by taking actions and making observations and enjoying rewards. One version of the problem is the episodic reinforcement learning problem, where the interaction with the environment ends at some point in time. Could be a random time, tau, but ends at some point in time. And then the agent starts another episode afterwards, right? Again, interacting with the environment over time until that episode ends, et cetera. Right? Interacting with the same environment each time. Now, this is a special case of the general exploration problem, turns out. And the way to see that is, in the general exploration problem I defined, you take an action, you pass it through a channel, you take an action, you pass it through a channel, et cetera. Oh, and I should have mentioned, the channel's memoryless. The channel's memoryless. But reinforcement learning is a special case of this, where you can think of the channel as being your environment. You can think of your action as being the policy you apply over one episode of interaction. And you can see the observation as being through trajectory you observe through that episode, okay? and the reward being the sum of the reinforcement learning reward realized over the episode. All right, so reinforcement learning algorithm can be thought of as a special case of that general exploration context. And a reinforcement learning algorithm takes all the data you've seen over L episodes and produces a policy that you're going to use in the next episode. Okay? Special case. One algorithm that's studied in the reinforcement learning literature is called PSRL, or Posterior Sampling for Reinforcement Learning. All that is Thompson sampling applied to episodic reinforcement learning. So here, if we think of the environment as being parameterized by an unknown parameter theta, PSRL samples the environment from the posterior of what theta could be, and then in each episode follows a policy that's optimal conditioned on that sample, conditioned on that being the true environment. All right, in doing this, when the agent samples an environment and wants to follow an optimal policy for that environment, it has to compute an optimal policy, and that might involve viewing the environment as an MDP, where the state is a sufficient statistic of the history, and using dynamic programming to compute an optimal policy. Right? And when you do that, you could think of what you're doing as solving Bellman's equation, right, to compute a value function, and then using the value function to control the system. The Q star SA here is a optimal value of state action pair SA. All right. Okay, so does PSRL achieve deep exploration? Okay, so what's PSRL? PSRL is Thompson sampling applied to the episodic reinforcement learning problem. This information-theoretic mumbo-jumbo seems kind of abstract. It sort of suggests that Thompson sampling is a decent exploration heuristic. But does Thompson sampling really do what we're setting up to do with reinforcement learning with this deep exploration? Right, and the answer is yes. And one way to see that is you can actually prove strong regret bounds for tabular Markov decision problems for PSRL. But intuitively, it's actually kind of obvious that PSRL should be doing deep exploration. How do you see that? Well, let's come back to our problem of a mouse with a maze. Right? So the mouse comes to the maze. It knows what's in the white part. It doesn't know what's in the shaded part. What does the mouse do? Well, with PSRL, the mouse samples an environment from its posterior distribution and then applies an optimal policy for that sampled environment. What does it mean to sample an environment here? Well, its posterior essentially says, I know what's going on here, but I don't really know what's going on here. So when you sample, the mouse might roll a die, and based on the outcome of that die, decide what's in the shaded part of the maze. Right? Got a poor outcome for the die here, and so it's going to decide that the maze, the shaded part, looks bad. It's going to be pessimistic. And on that day, it's going to operate as though that's a true environment, and in that environment, it would make a beeline for the cheese. Right? The other possibility is that the mouse gets a positive outcome and decides to be optimistic about what it doesn't know about. Right? And when that happens, the mouse makes a beeline for the gray area, and therefore makes sure it learns something, right? So PSRL does deep exploration because it avoids this sort of stuff. It avoids dithering in the white area. All right. So I'm running out of time. I thought I'd have a bit more time than this, but let me say an important area for study in this topic is coming up with scalable, practical approaches that can be applied to very large-scale problems. And to develop such approaches, we typically move to model-free reinforcement learning algorithms, because in model-free reinforcement learning, after you learn a model of the environment, you're not stuck with an intractable dynamic programming problem, but rather you immediately know how to take actions based on that model. And what we've been developing in my group, as an example of this, is an approach that tries to approximate the posterior distribution over Q star, the posterior distribution over value functions, right? And the general approach is based on building on top of typical reinforcement learning algorithms. So there are these reinforcement learning algorithms of the kind that are studied in the neurodynamic programming book, the most popular algorithm of which right now is called DQN, Deep Q networks, which basically fit a neural network to approximate Q star, right, given the data you've observed over some number of episodes. All right, so these algorithms, and like DQN in particular, one interesting thing about DQN, by the way, is when you talk to high school students today, many of them know what DQN is, and many of them have downloaded DQN software and tried it out, even though they don't know what Markov decision processes are or don't know what dynamic programming is. Okay, so that's the level of popularity these things have achieved. But DQN generates a point estimate of your Q function, given the data you have so far, right? And what we want instead of a point estimate is a posterior distribution, right? Or at least the ability to sample from a posterior distribution. The question is how you pile technology on top of DQN to sample from a posterior distribution. And there's a number of ways to do this. One way is sort of like doing a particle filter, where instead of applying DQN once to your data, you add noise to the way it learns so that DQN sort of does something random. And you do that across many instances of DQN. So you have these sort of many DQN agents simultaneously learning from the data as it's generated. And this ensemble of DQNs represents sort of an ensemble, sort of a particle filter with each particle is a neural network that can be sampled to generate policy for the next episode, much like posterior sampling would. All right. Okay, so I just had this. Okay, so this is the demo I showed you earlier. Basically, with that kind of an approach, within about 1,000 episodes, you learn how to balance a pole, right? But with DQN, using dithering exploration, you never get anywhere. Okay, this with sparse feedback. Okay, so these sorts of algorithms also lend themselves to distributed exploration across many robots, where you can have robots diversify what they're doing and combining the data in real time and all learning much faster. And it's sort of interesting when you apply these algorithms that way to a farm of 100 robots to learn how to balance this pole with sparse reward. So it turns out that you can learn to balance this pole in one episode of one 30-second episode. You don't even need multiple episodes for doing this. Okay, so that's pretty cool. And this is real-time learning of how to balance this pole, given that bit of sparse feedback. Okay, so I think I'm out of time, but let me just say that Thompson sampling is just one heuristic for using quantification of epistemic uncertainty in order to guide exploration. But at some level, this is the important thing. In order to do efficient exploration, you have to be estimating epistemic uncertainty and using that to guide decisions you're making. Right? You can't just be making decisions based on point estimates and adding noise. Okay? And Thompson sampling is sort of a really simple heuristic that lends itself to a scalable implementation. But there are algorithms that are actually better than Thompson sampling on complex problems. And I think an important area of inquiry is to understand more about that and just how well we can do with something like a neural network. And I don't have time to talk about this here, but here's an example of a problem where Thompson sampling performs very poorly. Right? As I mentioned before, Thompson sampling does very well with linear models, but with a sparse linear model, you can show that Thompson sampling is a bad idea. Okay? And there are alternative heuristics that might be much better ideas to use with something like a sparse linear model. All right. Just a plug. One thing I found in this area is the theory is very difficult, and it takes us 10 times, even 10 years, to make incremental progress on the theory in this area, which I think is worth doing and which I've been doing. But on the other hand, in the tinkering and applied space, people are doing this super impressive things. And somehow, we need to bridge this gap and offer more insights to deal with the data efficiency issues over here. So one thing that I released with a bunch of other people recently is a tool called bsuite, which is a computational tool that is not meant to take a huge amount of computation and solve the huge challenging problems that are impressive, but where it's hard to learn something from what you're doing, right? It's meant to you represent a carefully selected portfolio of problems and ways of doing experiments that can help us learn and generate insight about reinforcement learning algorithms, much like we would from doing theory, except much faster. Okay, so if you guys should check this out if you're interested in reinforcement learning research. All right, so I showed you this timeline earlier, projecting forward. Dimitri writes books so quickly that as soon as this became a hot topic, like 2 years later, there's a new book by Dimitri on it. But just projecting forward, given that he's written a book and generalizing from the past, I'll say it'll be forgotten in 2030, but then be the basis of AGI in 2040. Okay, thank you.
Thank you so much, Ben. And we are a little over time, but if there's a quick question that we can handle in the 1 or 2 minutes, we could take it. Is there a quick question in the audience? There's one over there. Could you go to the microphone? Thank you so much.
Thank you for your interesting talk. So how about integrate genetic algorithm or evolution algorithm to the ensembles of agents to enhance the reinforcement learning?
I'm sorry, could you repeat that question?
Integrate genetic algorithm or evolution
algorithms.
Algorithm.
Got it. I mean, maybe I don't know that much about genetic algorithms, so there may be potential there, but I haven't thought about that.
Thank you.
Okay, thank you. In the interest of time, I'm going to suggest we thank the speaker again.
Thank you.
And